I know, it sounds totally nuts, right? But believe it or not, it's true. And the story of how we figure that out, well, it's one of the greatest detective stories in all of science. It's this incredible journey that takes us from, just a philosophical guess way back when, all the way to the super weird and wonderful rules of the quantum world.
So today, we're going to put on our detective hats and solve this mystery together. We'll go clue by clue, tracking down the evidence that literally changed everything we thought we knew about the universe. And honestly, that's what we love to do here at Learn with Ease.
Our whole mission is to make chemistry just click. We break down these huge ideas into really clear, simple steps. Seriously, our goal is to get you from the very basics to feeling totally confident about this stuff. All right, are you ready? Let's get into it.
Okay, so here's our game plan. We'll start with the very first idea of an atom, then follow the trail to find its tiny little parts. After that, we uncover a totally surprising empty space, figure out where the electrons actually go, and then land on the kind of fuzzy modern picture of the atom, and of course, why this whole journey even matters.
All right, first up, our story doesn't start in some high-tech lab. Nope, it starts way, way back. I'm talking over 2,000 years ago, in the mind of a philosopher in ancient Greece. So this guy, Democritus, he had this really cool thought experiment. He was like, okay, imagine you take something, anything, and you cut it in half. Then you cut that half in half, and you just keep cutting. Will you ever get to a point where it's so small you just can't cut it anymore? And his answer was, yes. He called those final uncuttable pieces atomos. I mean, what a brilliant idea, right? But here's the catch. He had zero evidence. It was all just a philosophical idea. And so for centuries, that's all it was, a cool thought. So for over 2,000 years, nothing. The atom is just an idea. Then, bam, 1808. An English schoolteacher named John Dalton basically reopens this super cold case, but this time he comes with receipts, actual evidence from chemical experiments. He said, okay, atoms are real, and they're like these tiny, solid, indivisible spheres, kind of like little billiard balls. He figured all atoms of one element, say gold, are exactly the same. But a gold atom is totally different from a carbon atom, and they combine in these nice simple ratios. That's why water is always H2O, never H2.50. And just like that, the atom wasn't just an idea anymore. It was a real scientific theory.
Now, Dalton's model, it was a massive step forward, but the case was far from closed. In fact, the next clue that came along was about to blow the whole investigation wide open. Turns out that uncuttable atom could actually be cut.
Fast forward to 1897. A physicist, J.J. Thomson, is playing around with this gadget called a cathode ray tube. Just picture a glass tube with all the air pumped out. He zaps it with electricity and sees this mysterious glowing beam. So he brings some magnets nearby, and he realizes this beam is actually made of tiny, negatively charged particles. But here's the kicker. It didn't matter what metal he used in his experiment, he got the exact same particles every single time. And that could only mean one thing. These particles had to be a basic building block of all matter. He had just discovered the electron.
Okay, so this discovery creates a whole new puzzle, right? If atoms have these little negative things inside them, but we know atoms are neutral overall, well, there has to be some positive stuff in there to balance it all out. So Thomson came up with this idea. He imagined the atom was just a sphere of positive pudding with these negative electrons dotted around inside, kind of like raisins in a pudding. And yeah, they called it the plum pudding model. It's a pretty good picture, but it was about to get totally demolished by our next detective.
All right, let's jump to 1911. A scientist named Ernest Rutherford, who is actually one of Thomson's old students, decides, you know what, I'm going to test this plum pudding idea. And what he found, well, it changed physics forever. His experiment was so clever and so simple. He basically built a little particle gun that fired a beam of tiny positive particles. They're called alpha particles, at this super, super thin sheet of gold foil. I mean, we're talking just a few thousand atoms thick. Now, if the plum pudding model was right, those little particles should just blast right through, like shooting a BB gun at a piece of cake. And yeah, most of them did go straight through, but some didn't. Some got knocked sideways. And a very, very tiny number, like 1 in 8,000, bounced almost straight back. Rutherford was completely floored. He famously said it was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. That just shouldn't happen. Clearly, something incredibly small and powerful had to be hiding inside that atom. He realized the only possible explanation was that the whole plum pudding idea was just wrong. The atom wasn't some soft, squishy pudding, no. It had to be almost entirely empty space. And all the positive charge, and pretty much all its weight, had to be crammed into this tiny, dense little point right in the middle. He called it the nucleus. And the electrons? Well, he figured they must be flying around that nucleus, kind of like planets orbiting the sun.
But of course, there was a problem. This new planetary model had a huge flaw. Based on the physics everyone knew back then, an electron orbiting like that should be constantly giving off energy. It should spiral into the nucleus and, poof, the atom would collapse in less than a second. But atoms don't do that. They're stable. So what gives? It was time for our next detective to step in and basically rewrite the rulebook.
So in 1913, a Danish physicist named Niels Bohr comes along with this totally radical solution. He basically says, hey guys, maybe the normal rules of physics just don't apply inside an atom. He proposed that electrons can only exist in these very specific, fixed orbits. He called them energy levels. And in these special orbits, they could just cruise around without losing any energy. They were like safe zones. As long as an electron stays on its approved track, it's totally stable and won't crash.
And this is where the ladder analogy comes in, which is just perfect. Think of those orbits like the rungs on a ladder. An electron can be on rung 1 or rung 2, but it can never just float around in between the rungs. Now, to jump up to a higher rung, it needs to absorb a very specific amount of energy. And when it falls back down to a lower rung, it spits that exact same amount of energy back out, but as a little packet of light, a photon. This, by the way, is the perfect explanation for why different elements glow with their own unique colors when you heat them up. It's those electrons jumping and falling.
Bohr's model was an absolute game changer. It worked perfectly for hydrogen. But when you tried to apply it to more complicated elements, things started to fall apart. And it still didn't really explain why only certain orbits were allowed. So, it's time for the final chapter in our detective story. And this one takes us deep into the weird, weird world of quantum mechanics, where things stop being certain and start being probable.
So by 1926, physicists like Erwin Schrödinger figured out that you just can't think of an electron as a little ball zipping around on a track. It's weirder than that. It acts like both a particle and a wave. So Schrödinger's model says forget about knowing exactly where an electron is at any given moment. You can't. The best we can do is describe this fuzzy 3D region of space, called an orbital, where the electron is most likely to be found. A good way to think about it is like a photo of a spinning ceiling fan. You can't pinpoint one single blade, right? But you can see the blurry circle where the blades are. That blurry circle is kind of like the electron orbital.
So there you have it. From a solid, uncuttable ball to this fuzzy cloud of probability. What an absolutely incredible journey of discovery, right? But why does any of this matter? Why should we care about this atomic detective story today?
Well, for one, it's a perfect example of how science really works. It's not about finding one final, perfect answer. It's about constantly building better and better models as new clues, new evidence come to light. And on a practical level, understanding the atom it's the foundation of everything. All of modern chemistry, biology, how we make new materials, it all comes back to this. And that tiny little electron that J.J. Thomson found, its discovery led directly to pretty much every single electronic device you've ever used. Your phone, your computer, all of it.
This whole journey from a solid ball to a fuzzy cloud, it's really a story about human curiosity. Every single model was a revolutionary leap forward for its time, built on the clues uncovered by the previous generation. And it kind of makes you wonder, doesn't it? After over 2,000 years of change, what do you think we'll discover next? What's the next mind-bending clue about reality that's just waiting for us to find?
Hey, if you had fun cracking the case of the atom with us, do us a huge favor and hit that like button. Share it with a friend who might find it interesting, and definitely subscribe to Learn with Ease for more explainers that make chemistry simple. Thanks so much for watching.